Hi, welcome back. So in this part of today's lecture, we're going to be talking about the derivative of the exponential function. So the function that we care about is f of x equals e to the x. So we care about the base of e. And the graph of this function looks something like this. Oh, I don't want to draw that there. I need to move it over a little bit because there's graph here on the left side. So our graph of our exponential function is kind of flat, and then it hits the y-axis and pops up. And our graph of e to the x crosses the y-axis at a y value of 1. That's a 1, not a 7. Okay, now you might be wondering why we care about a base of e, because e is that kind of weird number. It turns out that the exponential function that has a base of e has one really cool property that is really important when it comes to calculus. And I'm going to write it down, and then we'll talk about what it means for us. So f of x equals e to the x has the cool property that at every point on the graph, the height of the graph, meaning the y value, has the same value as the slope of the graph. I mean, that is pretty weird. This is the only function in the whole world that does this. So for example, here at x equals 0, the height of this graph is 1, and if I were to draw a tangent line at that point, the slope of that tangent line is also 1. If I pick any other x value and I draw the tangent line, the height of the graph is exactly the same as the slope of the graph at that point. Base e is the only one that makes that true. So why is this important? Well, let me read this sentence again. Every point on the graph, the height of the graph has the same value as the slope of the graph. That sentence tells us our derivative rule for e to the x. If f of x is equal to e to the x, then f prime of x is equal to e to the x. The height of the graph and the slope of the graph are exactly the same thing. So check this out. I just took a derivative and I wrote down the exact same thing. This is our derivative rule for e to the x. It is so easy that it can be hard. By the way, that also means that you could take a second derivative. So the derivative of f prime, equals e to the x is e to the x. So the second derivative is e to the x. The third derivative is e to the x. The fourth derivative is e to the x. The 2,500th derivative is e to the x. Okay. All right, so that's our new derivative rule. And let's look at some examples of calculating derivatives that involve this exponential function. So we are going to find the derivative. In our first example, we have y equals 5e to the x plus 32. So when we take our derivative, I see a plus sign here, so I can focus on 5e to the x, take its derivative, and then take the derivative of the 32. So for the 5e to the x, I have a number times our function, so I carry along the number, and I take the derivative of e to the x. Well, the derivative of e to the x is e to the x. So the derivative of 5e to the x is 5e to the x. And then my derivative of 32 is 0. I don't have to write the plus 0, but I can if I want. Okay, so that's our derivative. A second example, maybe we have a function named g, and g of x is equal to e to the x divided by x to the fifth, and we want to find the derivative. Okay, so the first thing I notice is that I have division, so I have a high function and a low function. I'm going to use the quotient rule to find my derivative. Okay, so the quotient rule says low d high minus high d low, draw the line and square below. So low, that's our x to the fifth. D high, the derivative of e to the x is e to the x. So low d high minus high e to the x. D low, the derivative of x to the fifth is 5x to the fourth. So we have low d high minus high d low. Draw the line and square below. So we have x to the fifth squared. So there is our derivative. If you are super excited about that derivative, you might want to clean it up, but it's certainly not required. Okay, so one final example of practicing with these derivatives. We have f of x is equal to e raised to the 2x to the third plus 4x. All right, now this is a little bit different because the power up here, the part that has the variables in it, is fancier than just an x. And so, kind of like with our natural log function, when we have something fancier than just an x, we need to apply a chain rule. So there's a special chain rule for exponential functions, and here's how it works. If y equals e raised to something fancy, in other words, e is raised to something fancier than just a plain old everyday x, then our derivative is going to be copy down exactly what we have up here, e to whatever the fancy stuff is, times the derivative of d over dx, the derivative of that fancy stuff. Okay. All right, so for our example, what that means is our derivative of e raised to fancy stuff is going to be e raised to that fancy stuff. So I copy this down exactly as written, and then times the derivative of that fancy stuff. So the derivative of this fancy stuff, the derivative of 2x to the third is 6x squared, plus the derivative of 4x is 4. So e raised to the fancy stuff, its derivative is copy down the original function exactly as is, and then times the derivative of that fancy stuff. Okay, so that's our last example of straight up finding some derivatives. I want to now do an example where maybe we actually have some meaning behind this log function or this exponential function. All right, in this example, we are going to talk about future value. Future value for a continuously compounding interest future value for continuously compounding interest is given by the formula P of t is equal to P naught e to the RT, where P of t is the amount in dollars at time t years. P naught, or P sub 0 is another way to say that. P naught, the naught is not spelled N-O-T, it's not as in N-A-U-G-H-T, as in it is, I can't even think of a sentence for it right now, but it's N-A-U-G-H-T. So it's P naught or P subscript 0. Okay, so P naught is the initial investment, and R in that formula up above is the interest rate as a decimal. Okay, so before we actually ask the question for this problem, let's back up and talk about some of this information up here. Future value for continuously compounding interest is given by this formula. Some people call this the PERT formula. And when we talk about continuously compounding interest, when you talk about compounding interest, you can talk about compounding one time annually, maybe 12 times annually, which would be monthly, or you could compound interest daily or hourly or every minute. And the idea is if you then talk about compounding your interest every second or every millisecond, then you kind of have this default of continuously compounding interest. And that gives us a really nice formula. You might remember if you took finite math last semester that when you talked about compounding interest and you compounded monthly or daily, that the formula looked really, really ugly. But when you talk about continuously compounding interest, you get this exponential function, e raised to, that t is your variable in your exponential function. You get this nice PERT formula, which is a lot easier to work with. Okay, when we talk about future value is another way of saying the amount of money at a given time, in probably predicting into the future. Okay, so what is our question for this particular example? If $700 is invested at 3% interest, that is not a reasonable interest for this current time period, but we're going to go with it. So $700 is invested at 3% interest. At what rate is the money in the account growing at 2 years and at 25 years? All right. So the question that we're being asked about is at what rate something is happening. So we're talking about, we want to know how quickly our money is growing, and that's important. But to come up with a rate means we're talking about a derivative. So we're eventually going to want to take a derivative of some formula. So what do we have here? Well, we have a continuously compounding interest PERT formula, and we have specific information that we can fill into our PERT formula. So let's start by doing that. So we have P of t equals P naught e to the RT. in our example, we're told that $700 is invested. So $700 is our initial investment, or our P naught. And this is invested at 3% interest. And we're not told over here that we have continuous compounding, but we're going to assume that that's the case. Okay, so our R value is 3%, and we're told that R should be written down as the interest rate as a decimal. Okay, so our R value of 3%, we want to write as a decimal, and so when I have a decimal, I move the decimal over by 2 places, and so my rate is 0.03. Okay, so that's our issue here. We've used the word rate in 2 different ways. We have our interest rate, which is not thinking about a derivative, that's our interest rate. And then we have our rate of change, or our growth, which is our derivative. So rate is being used in 2 different ways in this problem. Okay, so here is our P of t equals 700 e to the 0.03 t. So this is our formula, which says if I want to know how much money my account will have in 2 years, I plug 2 into this formula. The question we're being asked is, at what rate is the money in the account growing? So we need a derivative of this formula. We want the rate at which our money is growing. So P prime of t says, all right, I want to find the derivative of 700 e to the 0.03 t. All right, that's fine. I have a number times e to stuff, so I copy down the number, 700. And then when I take the derivative of e to the 0.03 t, what I see up here is this thing is fancier than just a variable. So I need to think about using that chain rule for e to the fancy stuff. So our derivative of e to the fancy stuff is copy down what I have up here, exactly e to the 0.03 t times the derivative of that fancy stuff. And the derivative of 0.03 t is 0.03. Okay, so I carried along the 700 because it's a number times our function, and then I took the derivative of e to the fancy stuff, and the derivative of e to the fancy stuff is copy down e to the fancy stuff, and then multiply times the derivative of that fancy stuff. Okay, so that's our derivative. I'm going to clean this up just a little bit. 700 times, I can multiply the 700 and the 0.03, and you should double check this, but when I did it on my calculator, I got 21. So I have 21 e to the 0.03 t. So this is our derivative. And now we want to answer the questions, which is, what is the rate of growth of our money at 2 years and at 25 years? So we're going to be plugging 2 in for t into our derivative. So for part A, at 2 years, we plug 2 into our derivative. So that gives us 21 e to the 0.03 times t, and t is 2 in this case. And now I want to type that into my calculator. Now, be really careful when you do type this into your calculator. You have 21, and then you have an e, and depending on which version of the calculator you have, it's either going to put a caret, or it's going to sort of make a superscript on there. And if it gives you the caret part, then make sure that you put this whole power in parentheses, so you would have 0.03 times 2 inside the parentheses. Otherwise, only the 0.03 goes into power. So make sure you put that whole power in parentheses. All right, so once you type that in, you should check that you get the same thing that I do. What I got when I typed it into my calculator is 22.3. All right, so let's talk about what this number is. This is the derivative of our function when we plug in 2 for t. All right, now, to understand what this number is saying, it's important to have a label here. And when I think about the label, we're talking about a derivative, which is slope. The input into our function is t, which is time, and that is measured in years. And so that's our run part, is years. And the rise part is our function that we're measuring is how much money, and we're measuring money in dollars. So our rise over our run, the rise is dollars, and the run is years. So our label on this is $22.3 per year. So what this is telling us is that at, or I should say 2 years, after $700 is invested, the money in the account is growing at a rate of $22.30 per year. Another way to say that is, roughly speaking, that in that second year, in year 2, your money in your account is going to increase by $22.30. All right, so that's part A. Part B, when t is equal to 25, we plug 25 into our derivative, and we have 21e to the 0.03 t, and t in this case is 25. Okay, again, you should type this into your calculator and make sure you get the same number that I do, but what I came up with is 44.46. And we're going to have the same label as up above, the rise, which is measuring dollars, over the run, which is measuring years. So this is $44 or $44.46 per year. All right, so think about this for a minute. When you invest $700, after 2 years, your money is growing at a rate, your investment is growing at a rate of $22.3 per year. After 25 years of that money sitting in your account, your investment is growing at a rate of $44.46 per year. So the longer you have the money in there, the greater it grows each year. I don't know if you can see this, but this is Franklin, and apparently he has decided that he wants to talk about making money today. Okay, to wrap up this problem, I think it's worth our time to graph this function on a graphing calculator. And so something that you might do is to plot on your calculator the original function, which is p of t equals 700 e to the 0.03 t. I'll draw a picture of what I get when I graph this function. So the graph looks something like this. And maybe if you want to kind of get a similar graph to this, you might graph this function on the interval from 0 to 30. And so on the x-axis, we have t, which is measured in years since the initial investment. And over here at the end is 30 years. And on the y-axis, we have the amount of money in the account, and that is measured in dollars. All right, so if on your calculator, when you graph this function, you can hit the trace button, and if you type in t equals 0, then the height of the graph will be at 700. And this makes sense because that's your initial investment. That is what you have at time 0 years. Okay. Another way to get that 700 is plug in t equals 0 into the formula, and the output should be 700. If you plug t equals 2 into your calculator, then the output that you get when you use the trace function and type in t equals 2, the output that you get, or at least the output that I got, was I ended up with 743.29, and that is P of 2. This tells us that after 2 years, your account has $743.29 in it. Okay. Now, what we calculated is we calculated P prime of 2. This is our slope at this point. So if I draw a tangent line at this point, when t is equal to 2, this slope of that tangent line is $22.30 per year. Okay, so your money is increasing at a rate of $22.30 per year after 2 years investment. On the other hand, around 25 years, if you plug 25 into your original function, the output that you will get, and you should double check this either by using the trace function and plugging in t equals 25, or plugging 25 into this formula up here, and the output, or at least the output that I get, is $1,481.90. And so this is plugging 25 into our original formula. This says that after 25 years, your initial investment of $700 has now turned into $1,481.90. What we calculated over here is P prime of 25. That's our derivative. If I draw a tangent line at this point, the slope of this tangent line is P prime of 25, which we calculated to be $44.46 per year. And so this says that if you want to wait one more year, you're going to increase your account by about $44.46. So the rate of growth of your account in year 25 is $44.46 per year. So the moral of the story is the earlier you invest and the longer your money sits in the account, the greater your money is going to grow and the faster your money is going to grow in those later years. All right, thanks for listening. See you next time.